I'm now going to introduce my BIDS apps called Bloodstream and PETFit. So starting off with the raw pet data, we have our image file as a nifty, and we have the accompanying information in the JSON file. This is called a sidecar file. Then we additionally have our blood data in these autosampler blood TSV and manual blood TSV files. So in the autosampler blood file, we typically have time and whole blood radioactivity. And in our manual blood files, we typically have time, plasma radioactivity, whole blood radioactivity, as well as metabolite parent fraction. And we don't always have metabolite parent fraction for all of the time points. So we also don't have metabolite parent fraction and plasma radioactivity for all the time points of the autosampler. So the job with blood modeling is typically to model the quantities that we don't have at a high level of temporal granularity in order to infer from the measurements that we do have at a high level of temporal granularity what the other quantities would have been in order to get a combined quantity at the end. So we have our data source is the blood data, where we have measured data from metabolite parent fraction, from plasma radioactivity, as well as whole blood radioactivity. Then we perform modeling and interpolation of the metabolite parent fraction, of the blood to plasma ratio, of the arterial input function, and as well as the whole blood radioactivity in order to get a modeled interpolated arterial input function and whole blood radioactivity for the subsequent modeling. So if you would like to download this package or read the documentation, you can go to the relevant GitHub page, github.com/mathesong/bloodstream. So this is what Bloodstream does, and then PETFit will take the arterial input function and whole blood radioactivity curves after interpolation and combine that with the PET time activity curve data, which we will get from PETPrep. And by combining these three, we will use PETFit to perform the quantification. Now, if we go to our raw data folder, in this case, I've put it over here, we can see here are our data files. All right, so this is a data set which is available on OpenEuro, collected by Bob's lab, looking at the MC1 PET radioligands. So here we can see the data, and here is the derivatives folder. So in the derivatives folder, we have a PETPrep output. So what we will do is I've provided some tools over here. Here we can Docker pull. These are the latest versions of the BIDS apps. So if we Docker pull each of these, this is basically how we download them. This is how we download them, and then they run within their containerized application. So Bloodstream, if you look at the GitHub page, you can see exactly how to run this, but I've basically pasted the command over here. So Docker run, this gives us a port so we can talk to the app from our web browser, and we just basically fill in these points over here. So we basically say this is the BIDS directory and this is the derivative directory, and then we just copy the rest exactly from the function itself. So we paste this in here. All right, so now we're using the interactive mode. We don't need to use interactive mode. Interactive mode is useful for doing all of the configuration ourselves. The reason I've built the interactive mode, a lot of BIDS apps simply work on the terminal. However, with a lot of these tools, there are quite a lot of, or for kinetic modeling and blood analysis, there are lots of different options. And so specifying all of this on the command line over here is going to be very complicated. So I've built a web application where we can actually define a configuration file, which we can either run interactively or we can actually run after the fact. So we can define our configuration file first and then copy it to a specific location and then run it on a server, for instance. But in this case, I will simply run it from the app. So our parent fraction, so here we can subset the data. We can choose certain subjects. So maybe we want subject 1, 2, 3. In this case, I'll just do it for the whole sample. Sessions, we can restrict to certain sessions, certain traces, etc. So parent fraction, we can choose either a best fitting model or we can decide which model we'd like to fit. I've also included this hierarchical generalized additive model. This is a mixed effect non-parametric model, which I find pretty effective. So I will just use that here. Here we have the formula, which is actually appropriate, so we can leave that. But if you would like to get into doing this, into specifying more custom formula, we can. And you can either read up about how to use these hierarchical generalized additive models or get in touch with me and I can help you for your particular application. We don't want to do any time setting, that's fine. Our blood to plasma ratio, we actually don't need to fit the blood to plasma ratio here because we don't have any additional whole blood measurements where we don't have plasma, but we can fit a hierarchical generalized additive model here too, just for the sake of demonstrating it. And here we have a formula which applies here, but if you want, you can also get more you can customize this a bit too. Our arterial input function, by default we interpolate. We can also fit various models. In this case, I think we can just leave it at interpolation. We can also decide on weighting options, etc. Our whole blood, I typically advise against modeling the whole blood, but this can be useful when one has a high degree of when the blood volume fraction plays a large role in the measured time-activity curve, because the tracer maybe has low brain uptake, and when the whole blood curve is very noisy. So sometimes we might fit a spline to this in order to just smooth that out a little bit. But in this case, I think we simply leave this as interpolation. So we move to the last part. We can either download the configuration file. Here we've downloaded the configuration file. This can then be used for a non-interactive run of the command, but we can also just, while we're in the configuration app, and of course here is our configuration that we've specified, we just run the pipeline. So I will do that. Run. And it says running Bloodstream. So this will take a little while, so I will pause the recording. The app is now finished running. As we can see, it's closed in the browser as well. So we can now go to the folder. So here in the derivatives folder, we'd open here. We look in Bloodstream, primary analysis. We can have primary analysis, which is the default output folder, but we can also have secondary, tertiary, we can name it whatever we want. This basically allows us to do blood processing in slightly different ways if we want to check how much of an impact that has on the kinetic modeling. So within primary analysis then, within each subject folder, we have our input function, which is a very highly interpolated version at the time, whole blood, plasma, metabolic parent fraction, and arterial input function. And we have at a very, very, very high level of interpolation, which allows us, to use that as we need. So in our primary analysis, we also have a report where we can open here. We can see here is the model configuration. We can also view all of the code if we would like to generate everything, but for now I will hide it for now. Here is basically the configuration file, so we can see exactly what we did. Here we load the data, we perform quality control. There's no detected issues in any of these measurements. Now we have initial plotting. So these plots, just to explain, we see, maybe let me zoom in a little bit. We see, what I've done is I've shown all of these curves together. So the final arterial input function is the whole blood, is the plasma radioactivity, which is often derived from the whole blood radioactivity as well, multiplied by the parent fraction. So if we see something funny going on in the arterial input function, we can diagnose where it might have come from. So here we can see, here is the curves, here are the curves with time in absolute units, and here they are with a log scaled axis, so we can see, we get a much better view of what's going on in those early time points. The parent fraction then is normalized to 1, or is in its standard space. The blood to plasma ratio is also in its standard space, although if it's very much higher than 1, then it actually inverts it and calls it and shows the plasma to blood ratio. The arterial input function and blood curves are then normalized to 1 but relative to one another. So one can see that the arterial input function is higher than the blood, but it goes up to 1, which is 100%. So we can compare all of these curves within the same axes and figure out if something looks funny. So we basically look through these. These are all the raw data. All right. Then we can move along to, this is for the whole sample. We can move along to the modelling. So here we have the parent fraction modelling. In this case, we've done the HGAM model, the hierarchical generalized additive model. We can look at the residuals, the observed versus fitted values, the residuals, histogram and plots. We look at the average shape of the curve, as well as the deviations from the average curve. And then we have these individual fits for each of these individual parent fraction curves. So we have all of these, and we can check all of these to make sure that they look okay. Then we have our blood-plasma ratio. In this case, we didn't really need to fit the blood-plasma ratio because we have whole blood. We have plasma radioactivity and parent fraction. We have plasma radioactivity for all time points at which we have whole blood. But I fit this anyway just for the sake of demonstration. Here, once again, our residuals QQ plot, our residuals versus predictor, our observed versus fitted values, and our histogram. And we can see this is basically the estimated shape of the average function as well as the deviations from the average function. So as we can see, it looks about a bit wiggly, but we're between 0.675 and 0.725 here, so there's barely anything going on. We actually may as well have fit a constant here. So here are our average fits, which are basically constrained towards the average shape of this curve. And down at the bottom then we can see we've finished this. Then we don't do anything for the arterial input function or the whole blood, and then we do our final plotting. So here we can see, here are the data points, and here are our fits to those data points. So here, as I said, we may as well have used a constant value for the blood-plasma ratio, but here is now the parent fraction fitted, the blood-plasma ratio, as well as now the generated arterial input function values, as well as we haven't fit this. So now that we've used these parent fraction values, we have slightly different data points for the arterial input function. So if we saw something funny, we would be able to diagnose this. So basically this all looks good to us. And so we can proceed to the next step of fitting the model. All right, so we do all of this, and at the end of this document, it creates all the relevant outputs. It shows us some methods, code over here, or methods information. So we could, if we want, put this into our paper. We say, it says the parent fraction data was modeled using a hierarchical generalized additive model. Blood-plasma ratio was estimated using a hierarchical generalized additive model, and linear interpolation was used for the arterial input function of whole blood. So, and here is our session information. This shows us all the information about the packages used. So we can now proceed with the next step. So our next step then is, and just to say, so now we also have our configuration file. If we wanted, we could have generated a configuration file and saved it, and then without mode interactive, we could simply have run these steps and pointed it to our configuration file. You can see on the GitHub page exactly how to do that, and then it could be run in a non-interactive manner. So if you generate your configuration file once, you can then run this when you collect each new subject in your data sets, and it will just run exactly that configuration. So now